is the only one of these that doesn't require some other medium or contact, and that's how heat from the sun gets into our solar panels, it's how it gets into the house. But it's also one of the main ways that we lose heat into the environment is we radiate heat. My body is radiating, and anything cooler that's within line of sight of my body will radiate heat into. Typically, dark objects are better at absorbing that heat or radiating heat back to me if they're warmer than I am. For conduction, I should have mentioned that a rate of heat transfer is proportional to the temperature difference between two objects. Whereas for radiation, it's a bit more complicated. If you take the absolute temperature of the two objects to the power of 4, that determines the rate of heat transfer between the two objects. And then there's another, often it's considered a heat transfer mechanism, convection, but in fact it's a combination of conduction and mechanical transport, and it's when heat is conducted usually into a fluid, a liquid or an air, and then that air or liquid usually rises when it's heated, but it can have other turbulence in it, can be induced through a pump or through a fan, and heated particles or molecules are transported around, and this is what's known as convection. It's a very powerful method of transferring heat, but of these ones I've listed, it's very hard to model because it's quite complex. So one of the things that we want to do is control our heat loss. We want to control the radiative heat loss. Of all those methods I listed, the mechanical transportation is the easiest to control. And conduction, which is tightly coupled to convection, is the most difficult to control. And so usually some sort of thermal insulation is used to control heat loss. Some methods to minimize heat loss are to reduce the surface area of whatever you have that's heated, to reduce the temperature difference. So I mentioned that I could use cold water to melt ice, or I could use warmer air to melt ice. If I had those two systems, the cold water one will lose less heat to its environment. So if I had some large process with a lot of heat involved, if I can transfer heat at lower temperatures, I'm likely to lose less heat to the environment, so it will be easier for me to influence where the heat ends up. And the last one is increase the insulation thickness. I should have put also quality. If I had a higher quality insulation, it will reduce it. There's a couple issues with thermal insulation, and the biggest one is almost any substance that you name and classify as a thermal insulator is also quite a good thermal conductor, depending on your definition of thermal conductor. For example, if you consider R100 walls very well insulated walls, I did some calculations, I hope I got it right, but if I had a 10 by 10 by 10 cube, which isn't much bigger than the area we're in here, maybe a little bit taller, and you insulated all 6 sides, 4 sides in the top and bottom with R100 insulation, and it was a minus 40 degree day, which and 20 degrees Celsius inside the box, it requires 170 watts to keep that box at its temperature. Or put another way, it requires 4 kilowatt hours every day to keep that box at the temperature, or that box is going to lose 4 kilowatt hours every day, even though this is what I would think of in terms of housing insulation is quite a good level. I think for me this is a particular hang-up because my degree is originally in electronics, and in electronics we have a similar idea of conducting electricity, and we have electrical insulators. And so and it turns out that some objects that are good insulators and conductors of heat are similarly good insulators and conductors of electricity. For example, copper, in terms of elements, is one of the best conductors of both heat and electricity. Whereas dry air, especially if you can avoid convection, if you're just talking about conductive heat flow through air is one of the best insulators of air, of thermal insulators. And so I listed here different thermal conductive and electrical conductive values. And you can see if you get electricity, copper is a good conductor and air is a good insulator. The difference between those, the ratio of how good of a conductor air is to how good of a conductor copper is the magnitude of 10 to the 22nd. What is that? A billion, billion, billion? Whereas in the thermal system, those same two, like a really good thermal conductor and a good thermal insulator, it's only about 15,000 times better. And some substances, such as glass, we use it as an insulator, but it's only maybe 400 times better than what we're calling a really good conductor. So the range of materials for thermal insulators and conductors is a much smaller set, and it's very, in electrical systems, it's very easily to totally isolate you from electrical current with a very thin layer of rubber or just an air barrier, and you don't touch it. You don't have to be very far away, and the electricity won't get you at all. But for heat, you can have a relatively large thermal insulator, and heat will still flow. Now I want to talk a little bit about water and the different phases and states of water. Some basic numbers and data. So a liter of water and a kilogram of water are about the same. A liter of water weighs about a kilogram. And to heat that kilogram of water or liter of water requires about 1.1 watt hours of energy to heat at 1 degree Celsius. Or conversely, if you want to draw heat out of it, you can get heat at that rate, depending how many kilograms you have and how many degrees Celsius you cool it. Warm water rises, which can be very advantageous in our systems, but it can be trapped. So if you have a pipe, you can sort of get a localized high spot where the hot water will rise to, and then if you go low and high again, you've trapped your hot water, so you've isolated the effect of convection currents rising your hot water, which is also important to control heat loss. Freezing water at about 0 degrees Celsius. In order to freeze water, if you reduce the temperature of water, if you take energy out of water, the temperature will drop until it gets to the freezing point. And then you can continue to take out energy. You can take 92 watt hours out of your kilogram of water, and it will freeze, but the temperature won't change. It will stay about 0. Then once it's frozen, it will continue dropping in temperature again. And if confined, when you freeze water, it has an extreme expansive forces. So it's important anytime there's potential for freezing in the systems we deal with, we either have to eliminate the possibility of freezing or somehow be prepared to deal with those forces. And it's very, very difficult to try and contain those forces. So usually we prevent water from freezing. To do that, we use an antifreeze solution, and in the solar world, we use a non-toxic propylene glycol as our antifreeze. And for our systems here, we use 50% propylene glycol, which sort of gels, which means it becomes... Propylene glycol doesn't freeze the same way water does, where at 1 degree Celsius it's a liquid, and at -1 degree Celsius it's a very solid ice. This one sort of gels, and that starts around -35, and it becomes more solid. And at about -60, it starts to have these expansive properties, or expansive forces. But up in this whole range, -35 to -60, it's sort of safe, but not really liquid. Problems with the antifreeze solution is it doesn't hold much heat, or it's not as easy to pump when you compare it to water itself. On the other end of the scale, when you boil water at about 100 degrees Celsius, that requires even more energy. To boil that kilogram of water takes 361 watt hours. So I was saying down here that if I took